This is a look at the type of forces that we find acting between particles holding together a substance, and based on the relative strengths of these forces, that can help us predict what type of properties the substances are going to have. So is it going to have a high melting point or low melting point? It will have a large viscosity or low viscosity. So to start off with, we need to look at the two different categories. There's intramolecular forces, and those are basically nothing different than what we talked about before. We talked about bond types. So intramolecular forces are those forces that exist between atoms within a molecule or compound due to bonding. So we have the three types we talked about back in Unit 5, ionic, metallic, and covalent. And again, we'll see this from the activity that we're doing in class, but intramolecular forces are much, much stronger than intermolecular forces. So basically, if I have a substance that its melting point or boiling point or whatever is dependent on the intramolecular forces being overcome, they are more likely to have higher melting points, higher boiling points, etc. So let's take a look at the different types of intramolecular forces. First off, we've got ionic, and these are the forces of attraction between ions, and we talked about the fact that we've got positive ions and negative ions that result from a complete transfer of electrons. If you remember, we had talked about differences in electronegativities as a way of determining whether or not we've got ionic bonds or covalent bonds. And so when we had electronegativity difference that was greater than 1.7, that means that there's a big enough difference between the electronegativities of the two atoms that are bonded that one atom will completely take electrons from the other. So the atom with the larger electronegativity, which is going to be the nonmetal, will take electrons and become a negatively charged ion, and the metal will lose electrons and become positive. And so it's because of that positive and negative opposite charge that the two ions stick together, and that's the intramolecular force of an ionic bond. Notice that these are very, very, very strong intramolecular forces, so that's why we had talked about the fact that ionic compounds have very high melting points in Unit 5, and so notice that we've got, for each, this is a sodium ion that I circled there in the purplish blue color, each one of those positive ions is completely surrounded by these green negative ions, and so that means that the ions are very strongly attracted to their neighbors, and it's going to be very difficult and require a lot of energy to overcome those attractions and make changes in state of matter. Next, we've got metallic forces. So metallic forces are forces of attraction holding together metal nuclei. So these are neutral metal atoms. So again, it's a network of these metal atoms, and they've basically, they're sharing their valence electrons. Those valence electrons are free to move through the structure. That's what we said allows metals to conduct electricity in the solid state. If we are looking at the formula for a metal like this, so that's copper. If I see that formula, I know that those copper atoms are held together with metallic forces. Likewise, if I have any other elemental metal, so those are the elements to the left of the staircase, those are going to be held together by these metallic forces. Then lastly, we've got covalent forces, and we know that those are a result of the sharing of electrons between two atoms, and those can be equal or unequal, so polar or nonpolar, and we know that the difference in electronegativity between the two atoms in a covalent bond is going to be less than 1.7 in order for it to be covalent, and we know that if it ends up being less than 0.4, that's going to be nonpolar, and if it's greater than 0.4 but less than 1.7, that's going to be the polar covalent, and we'll talk about that again when we get to the next slide involving intermolecular forces. So again, intramolecular forces are basically the same three bond types that we talked about earlier in the year, and that would be ionic, metallic, and covalent. So in comparison, we looked at intermolecular forces in our activity in class, and intermolecular forces are specifically between molecules. So they're forces of attraction between neighboring molecules. So the word molecule specifically is only allowed to be used for covalent substances. So what that means is this is only something, a type of force that's going to be present between something that's got covalent bonding. So if we've got something that's ionic, if we've got something that's metallic, intermolecular forces are not going to be discussed. It's going to be the strength of that intramolecular forces in ionic and metallic that determine the properties. In a covalent substance, we've got intermolecular. So intermolecular, those are the forces between. So the word between has some e's in it, just like the intermolecular, if that helps you remember that that's what we're talking about, between individual molecules, not what's holding the molecule together itself. These are going to be what determine the physical properties for a covalent substance, so we're going to look at the different types of these forces next. And another name that you might hear these referred to by are van der Waals forces, named for a scientist who first studied them. So we've got three types of intermolecular forces, and basically all three of them are variations of the same idea, and that is that we know that when we talked about a polar molecule, we said that in a polar molecule, like, well, let's say H2O. So I've got a hydrogen bonded to an oxygen, and then that's bonded to another hydrogen. And if you remember, actually, when we drew it back in Unit 5, we had drawn it, it's going to have that bent shape, and there we go. Okay, so when we've got a polar molecule, what we've got is an uneven or unequal sharing of electrons. The more electronegative element is going to have the partially negative charge, so we use this delta negative symbol for the partially negative, and hydrogen, which is going to have the lower electronegativity, has the partially positive charge. So polar just means that we have two oppositely partially charged ends of the molecule. So notice, like this depiction shows, we know this from previous science classes, but the negative end attracts to the positive end of a neighboring molecule, and so there's attraction between the particles because of the polar or opposite ends. So dipole-dipole is our first type of intermolecular force, and it's just that force of attraction between the oppositely charged ends of polar molecules. Our next type of intermolecular force are called dispersion forces. You may also see them referred to as London forces. And basically these are going to be between non-polar molecules. So the dipole-dipole forces were between polar molecules. These are between non-polar molecules. Notice it says small transient attractive forces. So what that means is normally we've got this non-polar molecule. So notice the greenish color is the electron density, and it's basically evenly distributed among among the two atoms in the molecule in this top unpolarized picture. But what happens is sometimes there's an occasional shift. So we know the electrons are traveling around the atom in these orbitals that we talked about earlier in the year, and they're going back and forth and back and forth. And every once in a while there might be just a second in time where the electrons are briefly shifted to one side of the molecule. So notice in this picture down here, we've got what we call a momentary dipole. Majority of the electrons have been shifted over to this side, and that gives them just temporarily this partial negative charge on that side, on that atom, and then leaving this side with a partial positive charge. Because of this molecule now having this temporary or momentary dipole, then it will actually affect a neighboring molecule. So this partially positive side then is going to attract the electrons from this neighboring molecule, and they'll shift over, and that also then causes what we call an induced dipole, meaning that it's being caused by something else. These forces are very weak because these are temporary, so these are much, much weaker than the dipole-dipole forces because they are only temporary, and these are occurring between nonpolar molecules. But we do find that these forces of attraction become stronger for larger molecules, and that has to do with the fact that they have a larger electron density, more electrons to shift, and therefore they can have an increased polarity if their electrons all shift in the same direction at the same time. Lastly, we've got hydrogen bonding, which is an intermolecular force also between polar molecules. So this is like a special extra strong version of dipole-dipole. Notice though the criteria is we've got to have a hydrogen atom bonded directly to a fluorine, oxygen, or nitrogen. Notice that these are the most electronegative elements in the table. So fluorine we know is the highest with 4.0, oxygen is 3.5, and nitrogen is 3.0. And so because those combine with hydrogen, those elements, without taking hydrogen's electrons completely, very strongly pull on the electrons that they're sharing, and therefore it's an extra strong, extra polar bond. So the hydrogen is, with the lower electronegativity, going to take on the partial positive charge. The other atom, either the F, the O, or the N, are going to take on the partial negative, and the oppositely charged ends of each molecule are going to be attracted to each other then, just like we saw with the dipole-dipole. Notice that hydrogen bonding, sometimes a misconception that people have is that we're talking about an actual bond to hydrogen. So this right here, showing the H bonded to the O, that's a covalent bond, but it's the attractions between neighboring molecules that the hydrogen bonding is. So hydrogen bonding is an intermolecular force. It's not the same thing as like a covalent bond with hydrogen, but it's an attraction between a partially positive hydrogen in one molecule and the partially negative end of another molecule. So we commonly see that in water, which of course is H2O. So we know we've got two H's attached to O's. Another example would be like HF, right? So hydrogen directly bonded to fluorine. Some other examples would be in ammonia. So ammonia is NH3. I would see the nitrogen bonded to three individual hydrogens. And so those all would be examples of something with hydrogen bonding. Something that's not hydrogen bonding is if I have something like this, where I've got, I happen to have oxygen present in the molecule, I happen to have hydrogen, but if they're not directly attached to each other, this molecule is not going to have hydrogen bonding. There would be a dipole-dipole attraction because we do have a polar bond between the oxygen and the carbon, but we would not have hydrogen bonding because the hydrogen and the oxygen are not directly attached to each other.